Welcome to day 29 of 50 days of tutelage. In today's class, I will be talking about pressure in fluids. Pressure in fluids. But before I start with pressure in fluids, I'm going to be introducing you to the concept of pressure itself. So, what is it about? And it's always very confusing sometimes when somebody says apply force and another person is saying apply pressure. Are they the same thing? Or what is the difference between the two of them actually? Can you use them interchangeably? Can you call them synonyms? Actually, no, you cannot. Because you see, it's one thing to be able to apply force, and it's another thing to be able to apply pressure. But one cannot function without the other. So before you say you want to apply pressure, you would actually need a force. But the only difference is that when you're applying pressure, you are actually trying to consider action of a force at a given area. Action of a force over a given area. So therefore, the impression of a force over a certain area is what pressure is all about. So force can do a lot of things. Force can cause an object to start moving. So if I impress a force on this body now, the body can start moving. So force can get a work done. It can drag an object from this place and drag it up to this point. Force can do all of these things. But imagine a force that is acting. In this case, it is not causing the object to move per se. Instead, it is just impressing the action on that surface. Then when that is happening, then we have what we call pressure. That is why pressure generally is given as the ratio of force divided by area. And this helps us understand that when you're applying a force on a given area, the higher the force, the higher the pressure as well. But the area, in the other hand, is inversely proportional to pressure, which implies that when you're applying a certain amount of force, if you apply it and you impress it over a small area, then the pressure will be great. But that same amount of force, if you apply it over a large area, the pressure is going to be very little. That is why if somebody is wearing high heel shoe, let me just draw what high heel shoe will look like. If somebody is wearing high heel shoe and somebody is wearing a flat shoe like this, and both of them are stepping on the same area, this person will exert more pressure because the high heel is actually covering a very small area while this one is covering a very large area. So in this situation, pressure will, if let's say the same person is wearing the shoe at different time, then they are exerting the same amount of force, but the areas are different. So therefore, their pressure will actually be different as well. So pressure is a function of the force, apply force, and also area as well. So force can do a lot of things, but when force is being impressed over a given area, that is when we talk about pressure. But today, I'm not really talking about the actual pressure itself. I want to talk about pressure in liquid, pressure in fluid. So what happens is that whenever you have a fluid, so let's say this is a container and you have a fluid in this place like this. Now, this fluid exerts a certain type of pressure. That is the pressure we call hydrostatic. We call it hydrostatic pressure. And this pressure has its property and the way it actually also acts. In this situation, we had already explained about the fact that force is being impressed over a given area. But when it comes to liquid, when it comes to fluids, pressure kind of behave in a different way. And I'm going to be giving you the details of everything in this particular class. So the first thing you need to note is that when you begin to place objects in this fluid, let's say you suspend an object A around here, you have an object B around here, you have an object C around here, and let's say you have object D around here as well. So what happens is that this object, as you begin to go down in the fluid, the pressure actually increases, which implies that at different level in this liquid or in the fluid, you will always experience different amounts of pressure, where you have the littlest or the smallest amount of pressure from the surface, and it increases as you go down to the extreme depth of that fluid. So pressure is always increasing with depth. But when you go from top to from bottom to top, then the pressure will be decreasing. The pressure increase or decrease. So it depends on depth. That is the first thing you need to take note here. So unlike this one I just explained now, it's just force impressed on on a given area. But inside the fluid, we have different levels, different layers of that fluid, and then pressure kind of it varies when you move across these different levels. The next thing that you need to also take note is that whenever you are at this depth, so this same liquid again, so I'm just going to bring it here, this same liquid. Now, if you place an object here, let's call this object A, object B, object C, object D, object E. Now, this object, they are at the same level in this fluid. Then we say that all of them experiences the same type of pressure. They experience the same what type of pressure. It doesn't matter the shape of the container. It doesn't matter what it looks like. They will always experience the same. In fact, let me show you something here. Let's say I have another container. I have another container here, and then it contains this same exact liquid. This same exact liquid. Can you see that? Like it's not different. The same liquid that is here. So liquid L1, liquid L1 as well. But what you notice is that this container is larger than this container. As long as the base of the container is here, and both of them, so I place objects at this same level in this container as well. Even though this container seems smaller, the pressure here will also be the same thing as the pressure here as well. So that is one thing you need to really take note about depth and pressure. Once it is the same liquid and you can measure the same depth, it does not matter the width of the container, the pressure will still remain the same. But now, what if you have liquid of different densities? So you have a liquid, so you have, let's say, in this place you have a liquid 1, you have liquid 2, you have liquid 3, and you have liquid 4. So permit me to just assume that the liquid is filled already. So when you have objects at different heights in this place or at different depth in this liquid, so you have an object here, you have an object here, you have an object here, you have an object here. So even if they are the same container and then the same level of fluid and everything, but because these objects, they have varying density, the liquids or the fluid rather, they have varying density, they are not of the same density. So if you call this one density 1, density 2, density 3, and density 4, what happens is that pressure is actually going to vary. It's going to vary with density in this different fluid. So the one with the higher density will have the higher pressure because you are in this fluid. You are in different fluids rather. So that is another thing that you need to always take note whenever you are dealing with pressure in fluids. These three things are always very, very, very important, and you need to take note of them. Another thing also you should also know is that in terms of liquid or in terms of fluid, there is always a kind of distribution of pressure everywhere. I've explained that, I'm just reiterating it. So there's kind of distribution of pressure everywhere. So you cannot be in a certain place in the liquid and you will not experience a form of pressure or the other. So let's proceed with what this is all about. But here's the thing. The pressure that you notice inside the fluid is one thing. But before you talk about the fluid, that is, in this case now, I'm talking about a liquid. At the surface of liquid, there's another fluid, which is the air, the atmosphere. So when you place any liquid, when you have any liquid of this sort in a container, so before you actually enter the liquid, at the surface, you have air flowing around. And this air is what constitutes what we call our atmosphere. This atmosphere is also a fluid and it also has its own pressure. This pressure is known as the atmospheric pressure. The atmospheric pressure is actually a pressure that is kind of measured at sea level. At sea level. So what happens is that inside this liquid now, if you go down to this depth, the pressure that you're going to experience will actually be a kind of net effect of both the atmospheric pressure and the gauge pressure that you will experience in the fluid. But also, if you decide to move above the liquid level, or we call it above sea level, you also experience a net pressure which is also a factor of both the atmospheric pressure and the gauge pressure that you're using to go up as well. So let's talk about this thing called total pressure. So if you want to determine the total or the net pressure in a system, it is actually the atmospheric pressure plus or minus the gauge pressure. This gauge pressure is given as rho gh. Rho is the density, g is the acceleration due to gravity, and h is the height or the depth, depending on which one we are dealing with. So it's going to be the atmospheric pressure plus or minus rho gh. And then I'm going to give you something. I'm going to show you how this rho gh is actually consistent with this other guy, pressure equals force over area. So we said that pressure itself is force over area. So I'm going to show you how consistent this is. So loosely, we know that force can be given as mass multiplied by acceleration. Mass multiplied by acceleration. So let's say this is divided by area now. Another thing we also know is that density equals mass over volume. And that implies that mass equals density times volume. So that implies that I can replace mass with volume. I can replace mass with density times volume here. But another thing again is that volume itself is area times height. Volume is area times height. So anytime you want to find the volume of a substance, it's always area multiplied by height. So in that situation, another thing is also note is that in this case, if I'm talking about this fluid now, the pressure that this entire container will exert, let's say on this surface, that is, if I'm impressing this pressure of this entire container on this surface, the pressure will actually be done by a force which is the force of gravity, and that is the weight. So therefore, in this case, the acceleration I'm considering will be mg. So therefore, pressure will now become, instead of mass times acceleration, I will have this entire thing will replace mass. That's rho multiplied by a multiplied by h, and a will be the acceleration due to gravity, and this is divided by area. So you have this cancelled out, and pressure is rho times h times g. So you can see where we get the rho gh from. That's our gauge pressure. Now, so total pressure is always the sum of the atmospheric pressure plus the gauge pressure. That is if you are going down. That is if you are covering a depth. But if you're going up, it's going to be different. So going down, you have PATM plus rho GH. If you're going up, you have PATM minus rho GH. And that is the concept of atmospheric pressure and gauge pressure. So it's always a net effect of everything. Now, let's talk about one principle. The principle is known as Pascal's principle. And what is Pascal's principle? Pascal's principle basically tells us that whenever we have an enclosed fluid, like you have a fluid in this container, so there's a fluid in this container and it's enclosed. So all the other ones I've been drawing since, they are not enclosed fluid. They are free, they are open to the atmosphere. But when you have an enclosed fluid as this, for instance, the sachet water, if you have sachet water now is an enclosed fluid. And if you apply pressure, let's say to one end now, you apply pressure to this end. What happens is that pressure is going to be transmitted throughout this fluid. From this point, it's going to be transmitted throughout the fluid and even to the container as well. So pressure, Pascal's principle just says that whenever pressure is applied to a confined fluid, it is transmitted equally in all directions. And you can try that with a sachet water. You can just take one and then try to impress a force on one end of the sachet water. You notice that the rest of the water, the rest of the container or the rest of the sachet will actually toggle up. And that is one way you can visualize Pascal's principle. So what are the applications of this Pascal principle? It's actually used in automobiles. So when you apply a car brake, it's actually like work based on Pascal's principle because there's something called a brake fluid. There's something called brake fluid. Yes, I think it's called brake oil. Generally, it's called brake oil. So this brake oil kind of help in transferring the pressure that you applied from the leg, using the leg from the brake pedal to the wheel as well. But I think the advent of electric vehicles kind of, stops that. But majority of the cars actually still use that today. So that's one of the application. Another application is the hydraulic press. So in the hydraulic press, we kind of use a lift heavy loads using the concept of pressure. And I'm going to explain the hydraulic press real quick. So this is what the hydraulic press looks like. You have something like this. Yes, something of this nature. So don't mind my diagram, it may not be that perfect. And then you have a fluid inside. So let's have fluid. So let's say the load that you want to lift is here. You want to lift a very heavy car. So I'm just going to draw what's a random car here. So you want to lift this car and then you want to apply pressure. What you do is that you come to this place. This is a small area and you apply a certain amount of force. So let's call this area 1 and let's call this F1. Then what happens is that based on Pascal's principle, when you apply pressure in this place, this thing actually moves down and it's impressed downward. So once that is happening, there is a kind of transmission of pressure. So pressure is transmitted undiminished. And this pressure sort of now make this guy to go up. So that implies that a new force is being applied on this. It's a kind of upward force. You can call that one F2. And it's been applied over this area. Let's call this area 2. But here's the thing. From Pascal's principle, the pressure that you applied here is the same as the pressure that you applied here. So that implies that in that case, F1 divided by A1 will be equal to F2 divided by A2. And so what you notice is that if they are going to give the same pressure, that means that the force you're applying here is actually smaller than the force that is being applied here. So you have used a smaller force, using the case of Pascal's principle, you have used a smaller force to generate a bigger force. And that is basically what the hydraulic press, that is basically how it works. So in this place, you have ratio of F1 over A1 equals F2 over A2. F1, the F1, A1, they are from the left limb, which are the smaller piston, which has the smaller piston rather, and then F2 over A2 is on the right limb, which has the larger piston. And that's based on Pascal's principle. Now let's move on to Archimedes' principle. But before I talk about Archimedes' principle, I will talk about buoyancy first. Buoyancy, which is also generally known as upthrust. I like the word upthrust anyways because it helps to actually properly view this whole concept. Now, what is upthrust and what is buoyancy? What happens is that whenever you insert a body or whenever an object finds itself in a fluid, it doesn't just, happen to just be like that. The first thing you notice is that upon entrance, the weight of this object is always acting downward. I think I've established that in previous classes. So the actual weight of the object is acting downward. But what happened to this person is that whenever this body enters a fluid, or whenever a body enters a fluid, the fluid itself we experience because it is do me, I do you. You are pressing down on me by your weight, so the fluid also wants to press upward on you. So therefore, it is giving you a thrust that is upward. So we call this guy upthrust or force of buoyancy. So the body is impressing its weight downward in the fluid. The fluid is also protesting and exerting a kind of thrust, which is what? Upward in the fluid. So here's the thing. The fluid is only reacting to the action of the weight of the body. So that implies that the upthrust that the fluid is actually exerting on the body, it cannot exceed that of the weight of the body. So in fact, the maximum that upthrust can be is being equal to the actual weight of the body, because it is a reaction. It's just like when a body is resting on a surface, like I've taught you earlier, there's weight acting downward and there is a normal reaction. That's the same thing with upthrust as well. So it cannot exert more than the weight that is being impressed downward in the fluid. So let's proceed. how does this upthrust, how does it now work? What exactly is it? As this body, this upthrust is being exerted upward, this body feels something. They feel weightlessness. Because the upthrust that is being impressed upward is actually reducing the reaction, how they feel as a weight. Now, in some of the previous physics classes, I've already explained the concept of weight. The weight of someone cannot actually change in the real sense. Or let me say the mass of someone cannot change. Let me not say weight. But in a certain space, in a certain place, a given place where you have acceleration due to gravity is constant there, the weight of this person cannot change. The weight of the person is always going to be a product of mass times acceleration due to gravity in that place. So the only thing that can make the weight change is acceleration due to gravity. But as long as it's not changing, the weight of the person remains the same. So which means that even inside this fluid, this person still has a weight of mg. Nothing is reduced. But here's the thing. What this person feel as their weight at a point in time, the reaction. So what you feel as your weight most of the time is a reaction. So that reaction that you feel is the net force that goes on in this place. Is the what? Is the net force. And that net force in this place is known as your weight in this fluid. That reaction, so that is what you will feel in this fluid as your weight, is weight in this fluid. So that weight in the fluid is always your actual weight minus the upthrust. Your actual weight minus the what? Upthrust. So what happens is that your weight in fluid is determined by the difference between your actual weight minus the upthrust. So that implies that when you have a lot of upthrust acting on you, that is huge upthrust acting on you, then it removes from your actual weight, and what you feel in the fluid, you are going to feel closer to being weightless. So that is what upthrust is. Apparent loss in weight. So its upthrust is the upward force that is exerted by fluid on a body, and it's also known as what? A kind of apparent loss in weight when a body is what? Being immersed in a fluid. So when you say apparent loss in weight, it doesn't mean that your weight becomes smaller. It's just that what you weigh inside the fluid, how you feel inside the fluid in terms of your body mass reacting with acceleration due to gravity is going to become lesser. That is exactly what upthrust or buoyancy is all about. So what is now this upthrust itself? Like I said, it's the fluid trying to act up on you. So one of the elements that this upthrust use is that since it's the action of the fluid, then it uses volume. And what volume? Volume of liquid displaced. So the volume of the liquid displaced is one of the things that is performing the action. So let's now see how this happens. Another thing also is also the mass of the liquid that was displaced. The mass of the liquid that was displaced. So therefore, let's look at this now. Upthrust is also a weight. So which is what? Or a force. Let me say a force now. Mass times acceleration due to gravity. But which mass? Is not the mass of the object. It is the mass of the fluid. Mass of the fluid that was displaced. So M here is the mass of the fluid that was displaced. But how do you calculate the mass of the fluid that was displaced? Like I already explained earlier, I said mass can also be written as density times volume. Density times volume. So therefore, what you have here is, you can now replace this with density. Density of what? Density of fluid times volume of fluid displaced multiplied by acceleration due to gravity. But how can you get the volume of the fluid displaced? The action of this object in the liquid, whether it is totally or partially immersed. So the volume immersed, volume of the object that is immersed will be the volume of the liquid that will also be displaced as well. So which implies that if 2/3 of the object was immersed in the fluid, so therefore the volume that you also have of the water that was displaced will also be 2/3 of that object that was immersed in the fluid. So that is how you determine that. So that is the concept of upthrust. And it is on this particular principle that we will build the Archimedes principle. Archimedes principle actually talks about the fact that when a body is immersed in a fluid, whether partially or totally, it experiences an upthrust which is equal to the weight of the fluid displaced. So that is what I just explained now. So upthrust is weight. So weight, what weight? Mass times acceleration is gravity. It is the weight of the fluid that was displaced in the process. And now, that now leads us to the principle of flotation. A lot of principle in this whole thing. Principle of flotation. What is principle of flotation? It simply tells us that for flotation to happen, there is going to be balance. So in this place, I already explained about the fact that upthrust is acting upward, weight is acting downward, and the maximum that upthrust can be is the weight. So what do you think will now happen if upthrust and weight are this? Because that's the thing about resultant force. Whoever has the higher magnitude will be the one to do the pulling to themselves. So if weight is more than upthrust, then the body will be going down. But here's the thing: if weight and upthrust, if they are the same, that means that nobody is pulling up, nobody is pulling down. So therefore, the body remains like this. So flotation, principle of flotation in summary is just upthrust being equal to the weight of the body. What the actual weight of the body. So whenever upthrust, so whenever your raw fluid, volume of fluid displaced times gravity is equal to mg, that is mass of object times acceleration due to gravity. When this happens, then you have flotation. So let's now define now. So this mass of object is equal to mass of fluid displaced. So therefore, a body will be able to float in a fluid if it is able to displace an amount of fluid that is equal to its own weight. That's just it. A body will be able to float in a fluid if that body is able to displace an amount of that fluid that is equal to its own weight. Because this is the equation of flotation. Equation of flotation is upthrust being equal to the weight of the body. So therefore, if you displace an amount of fluid that is the same thing as your own weight, then you float. And that is what the principle of flotation is all about. However, you can do this either by totally being submerged. So let's say this is the fluid. You can do this by totally being submerged. That is why a body can actually float just immediately under a fluid. But you can also do this by what? A part of you being what? Being submerged in the fluid. So, but once weight remains greater than the upthrust, you will always sink. You will always sink. So, lastly, what I want to explain is that this whole principle, how do you now apply it to make big objects? How do you apply it to make them float in fluid? The way we do it is that whenever you have a liquid, and you want to make it float, one of the things you can do is that you can decide to create a kind of voluminous space, something that is hollow, something that does not contain different elements. So when you create this now, something of this nature, and you create this object so that everything here is an empty space, hollow, then you now begin to build other things on it that are weighty. You begin to build other things on it that are weighty. This is my attempt in trying to build a ship anyways, so you don't have to mind that. And you put all of this on it. This hollow space, what it will do is that as it is being pressed down by this heavy object, is displacing a certain amount of the fluid. But because what is actually pressing down on the water is a big hollow material, so this thing will deceive the water and make you displace so much water now or fluid, such that this fluid will now be so heavy that the sum of the total weight of this fluid that is being displaced will now be the sum of the entire weight of this object altogether. So a proper calculation has to go in to determine, okay, which one is which, how do we create the hollow space, how do we create this thing, and all of those things. And that's basically what pressure in fluid is all about. I believe in today's class, I've been able to do a proper justice to the concept of pressure in fluid. So if you enjoy the class, why don't you just like the video and subscribe to the channel? I'll see you around.